Right, let me show you how to answer exam questions to do with electricity and circuits. I've took these questions from 4 past papers and you can see there's 51 marks. So this is a popular topic with examiners. Question 1. Figure 2 shows the junction of 3 wires F, G and H in a circuit. The current in wire F is 6 amps. The current in G is 3.5 and it wants you to calculate the current in H. So this is Kirchhoff's first law. What goes into a junction must come out. So 6 amps has gone in, 3.5 came out so far, so this must be 2.5. Because 2.5 plus 3.5 equals 6. Question 2. A wire in a circuit carries a current of 0.9 amps, so that's I for current. Calculate the quantity of charge, so that's C for coulombs, or rather Q for charge, that flows through the wire in 50 seconds, so that's T for time. And it gives us the equation, so charge equals current times by time. Let's just pop the numbers in. The current was 0.9 amps and the time was 50 seconds. Always make sure time's in seconds. And that equals 45 coulombs. Charge is always measured in coulombs. And you actually get a mark for knowing the units. Always make sure you know the units for all of these different quantities, as you can sometimes get a little cheeky mark for that. Question 3. The student investigates how the current in a lamp changes with the potential difference, so that's just voltage, across the lamp. The student uses the results to calculate the resistance of the lamp. The results are shown in the table in figure 17. So voltage, current and resistance. One value of resistance is missing from the table in figure 17. Calculate the value that's missing. So voltage equals current times by resistance. Therefore, resistance equals voltage over current. Make sure you can rearrange equations. Otherwise, you're going to drop marks. Use the magic triangle if you don't know how to do it. There's a divide by sign. Do a multiplied sign on the bottom to create 3 little boxes. The equation is I times by R, so put that in, I times by R, one space, one thing, shove it in, and then you cover up what you're looking for. So R is V divided by I. Right, pop the numbers in. So the voltage is 5 and the current was 0.26. And that comes out as 19.23 ohms. And we'll just round it up to 0 decimal places, or in this case round it down. Part 2. The student writes this conclusion. The resistance of the lamp is directly proportional to the potential difference. Comment on the student's conclusion. Use information from figure 17 in your answer. Right, that basically means you quote some values. Now it's worth 3 marks. So what I'll do is I'll say generally what we see. So potential difference is increasing and so is the resistance. So note that I'm talking about resistance and potential difference in me answer, because that's what they wanted us to talk about. Right, now they're saying directly proportional. Students often struggle to understand what directly proportional means. In a nutshell, if you double one thing the other thing should double as well. Or if you treble one thing, the other thing should treble as well. So it's not directly proportional. Because when I doubled one thing, the other thing didn't double. So that's 2 marks, and remember you get your 3rd mark, so this is where students miss out because they forget to quote the information. So, for example, when voltage went from 1 volt to 2 volts, resistance didn't double from 11 ohms to 22 ohms. And by the way, you could have picked any values. If I had have chose 2 volts doubling to 4, 0.14 should have doubled to 0.28, and it didn't. Question 4. A lamp is connected to a potential difference of 0.24 volts. So potential difference is just voltage, remember. The current in the lamp is that. So that's I. Calculate the power P. So it gives you the equation. I would always be writing down what you know when you know it. The little symbols that go with each value. So we just need to calculate the power. So just pop the numbers in. So that was 0.12 amps times by 0.24 volts. And I would always set it out as well. Equation, numbers with units, and then the answer with units. Then if you make a mistake by accident, at least you're still getting some marks for showing you're working out. And the answer is 0.0288. And that'll be in watts because it's power. Now, I often get asked, how many decimal places shall I do it to? Right, well, how many decimal places do they use? 2 for that and 2 for that. So I'll do mine to 2. So that'll round up to 0.03. But I would always leave the long version in as well, just to be safe. Part 2. The potential difference is changed to 0.3 volts, so that's our voltage V. The current in the lamp is now 0.13 amps, so that's I for current, and the lamp is switched on for 35 seconds, so that's T for time. Calculate the energy, so E is our target. That is transferred in this time. Select an equation from the list of equations at the end of this paper. Well, as I say to my students, Emma Dale is on ITV, which means energy equals current times by time times by voltage. So we'll just pop the numbers in. And that comes out as 1.365. And that'll be joules. And they've gave us that to 2 decimal places, 2 decimal places, 0 decimal places. So we'll do ours to 2 decimal places. Part 3. The current in the lamp stays at 0.13 amps, so that's our current again. Calculate the charge, so Q is our target. Charge that flows through the lamp in 35 seconds, so that's our time. And once again, they're giving us the equation. So Q equals I times by T. We'll just bang the numbers in. And that equals 4.55. And that'll be coulombs for charge. And I'll leave it at 2 decimal places, the same as them. Question 5. The student measures the current in the lamp for several values of potential difference across the lamp. Figure 13 shows the student's results. Now you'll notice that this is very similar to a previous question that I've just done. And that's the proof that you need, that by practicing these papers, it's the same questions that come up year after year, or very similar. Because remember, the questions that I'm going through now, these are from 4 different papers from 4 different years. So you can start to build your confidence when you realise, like, I've done this before. I know how to do it. The worst thing is if you go into the exam and you're trying questions that you've never practiced before. It can make you feel a little bit anxious, and that can affect your exam performance. So practice is the key. The student uses the results in figure 13 to write this conclusion. As the potential difference across the lamp increases, the current in the lamp increases, and the relationship is directly proportional. Look, this is what I'm saying. You should know how to answer this before I even go over it, all right? So that builds your confidence. Once again, it's potential difference, and it's the current this time, actually, before it was potential difference and resistance. And comment on the student's conclusion. Right, if it's worth 3 marks, we'll talk about the general relationship. So, as the potential difference increases, does the current actually increase? Yep. Yeah, it does, except for this last little bit, but that's fine. Right, is it directly proportional? Well, let's have a little look. Now, you'll notice that the values very conveniently double. So 0.06 doubles to 0.12. Okay, did the current double? So it should have went from 0.05 up to 0.10. Nope, it doesn't. Let's try this one. What about if we treble it? So 0.06 trebles to 0.18. Once again, very conveniently. So you'll start to see these patterns. That's all that an expert is. It's someone that's practiced something enough that they can spot patterns that other people, non-experts, can't spot. So that treble. Did this treble? Nowhere near it. 0.05 should have trebled to 0.15. So it is not directly proportional. And again, if you just left it at that, you'd only get 2 marks. So what do we do for our 3rd mark? We simply quote the data. So it should have doubled to 0.10 if directly proportional. Now, I'm usually pretty good at simplifying the answers, but that's the second time I've waffled on a little bit when it comes to directly proportional. I'm not sure if you can actually simplify it any shorter than that. You might find a way, but it makes me feel comfortable to know I've explained it fully. Question 6. A student is investigating a filament lamp. Complete the sentence by putting a cross in the box next to your answer. The current in the filament lamp is a flow of... Well, current's always a flow of electrons. Unless it's in solution, then it's a flow of ions, but that's more chemistry than physics. Part 2. The student uses this circuit in his investigation. Right, this is your standard circuit for getting the resistance of any component. So in this case, the component is a bulb. Now, if we're going to get the resistance, remember resistance is voltage over current. So you're going to need to measure the voltage. What do we measure the voltage with? We measure it with a voltmeter, and it always goes in parallel. So this here will be a voltmeter. And we need to measure current. So this will be your ammeter. that measures current. Ammeter has to go in series with the component. Now, just like a TV series, one thing comes after another, after another. That's why we say the ammeter is in series. And this is parallel, like railway lines on the metro or a train track. These lines never meet each other. So meter 1 measures current. So it's an ammeter, which is amps. Just putting current will be fine. And meter 2 measures voltage, otherwise known as potential difference. And it was a voltmeter. You don't need to put all that stuff. You could literally put voltage and you're fine. Now, how might they change this question for you? Right. Well, they might actually ask you to draw this circuit. So, make sure you've got that. If you want to know what's this thing, this is your variable resistor, and we do it so we can get multiple readings. If we change this variable resistor, we'll get different current and voltage readings, in case we wanted to plot a graph. Right, part B. The normal operating potential difference of voltage and current of the filament lamp is 6 volts, that's V, and 0.4 amps, that's our I. Calculate the energy, so that's our target, supplied to the lamp under these conditions in 20 seconds, that's our time. So as I said before, Emmerdale is on ITV. Emmerdale is like this soap TV series. Right, pop the numbers in. So current was 0.4 amps, times that by the time, which was 20 seconds. If they're going to be awkward, they'll put that in minutes. Always remember to convert it into seconds. And we need to multiply that by the voltage, which was 6 volts. And that equals 48 joules. So I've saw that question before as well. Part C. The graph shows how current varies with potential difference, voltage, for another filament lamp. So current up the side, potential difference or voltage along the bottom. Calculate the resistance, so that's our target, of the lamp when the current in the lamp is 0.3 amps. And it says resistance equals potential difference divided by the current. So R equals V divided by I. So R equals voltage divided by current. Now, they haven't told us the voltage yet. We need to get that from the graph. That's why they're giving us 3 marks. Right, we do know that the current is 0.3 amps. So the examiners love it. Go up to the current where 0.3 amps is, put dotty lines on, and then put some dotty lines coming down here. Now that's the voltage we're looking for. So 2 volts and 4 volts, so this must be 3 volts. So 3 volts goes in there, and if we do the calculation, that comes out as 10. And that's ohms. So always do the calculation. Don't think, oh, I know what the answer is. Always just pop it into your calculator just to make sure. I've saw loads of students over the years making mistakes because they're getting cocky. Right, question 7. The graphs show how the current in a component changes with the voltage across the component. Draw a line from each component to its correct graph. Right, the diode, yeah, that's that one. The resistor, fixed resistor, that's going to be this one here. And the lamp goes up like an S shape. So you've got to know what the current voltage graphs look like. Now, normally they do the negative as well as the positive. So if that's 0 there and 0 there, That's positive voltage and positive current. Now the diode, in the reverse direction, you get 0 current. And then once it gets to about 0.6 volts, then the current starts going up. A lamp, or as I say to my students, a bulb, or to be more precise, a spulb. And I call it that because it looks like an S shape. In the front, it goes like that, and then in the back, it goes the opposite like that. And then overall, it looks like an S shape. So that's why I call it a spulb, to help my students remember the shape. And basically, any fixed resistor is directly proportional, which means it's a straight line going forwards and in the reverse direction as well. Now we'll see if we need that later on in this paper. Question 8. A technician investigates the potential difference or voltage across an electrical heater. This circuit diagram shows the circuit the technician uses. Righty-ho. Add a voltmeter to the circuit, which will measure the potential difference across the heater. Right. Well, voltmeters always go in parallel, as I said before. The symbol for a voltmeter is a circle with a V. Part 2. The resistance of the heater is 15 ohms, so that's R. The current is 0.56 going through the heater, that's I. Calculate the potential difference voltage across the heater. So the voltage is our target. We don't know what it is. Okay, what's the equation? So V equals I times by R. That's Ohm's law. Current times by resistance. Now we'll pop the numbers in. And that equals 8.4 volts. Part 3. The technician changes the value of the variable resistor. She measures the new voltage across the heater and the new current in it. Here are the results. So that's the new voltage and that's the new current. Calculate the amount of electrical energy, so energy is our target, in 30 seconds by the heater. So time is already in seconds, that's great. Remember, Emmerdale is on IDV. Pop the numbers in. And that comes out as 72 joules. Remember, all energy is measured in joules. Part 4. The total energy supplied by the battery in 30 seconds is 144 joules. Explain why your answer in part 3 is not the same as the total energy supplied by the battery. Right, well, my immediate answer is you always end up wasting some energy as heat. Now, I know it is a heater and we want the energy as heat, but we'll also waste some energy in the wires and we'll also waste some energy in the variable resistor. So that'll get you the 2 marks. Question 9. A torch has a battery and a bulb. The current in its circuit is 0.08 amps, so that's current I. Calculate the amount of charge, so that's Q, is our target, question mark. Passing a point in this circuit in 2 minutes. I knew it. At some point they're being sly there. Right, remember you've got to convert minutes into seconds. So that's 60 seconds times by 2, which is 120 seconds. Right, and calculate the charge. Okay, so they're not giving us the formula this time. So Q equals I times by T. So make sure you do know your equations, or make sure you know to look them up on the equation sheet at the back of the paper. Right, pop the numbers in. So that's 0.08 amps. Times that by 120 seconds. And that comes out as 9.6 coulombs. Remember to know your units just in case they don't give you them. Question 10. Figure 18 shows a battery connected to a filament lamp. Explain in terms of the movement of charged particles how energy is transferred from the battery through the lamp to the surroundings. 6 marks. Right, this is one of those intimidating 6-mark questions where if you don't know how to answer it, you haven't practiced it already, you may struggle. So let me show you how I would do it. So in terms of the movement of charged particles, right, so we know that the charged particles are electrons, so I'm just going to put that down just in case I get marked for that straight away. Right, how energy is transferred from the battery through the lamp to the surroundings. So if I say a couple of things about the battery, there's 2 marks. Then if I say 2 more things about the lamp and then 2 more things about the surroundings, I'll slowly get to me 6 marks. Okay, so first of all, let's talk about the battery. Right, well, what type of energy is stored in the battery? Well, it's chemical energy, isn't it? So I'm going to say chemical energy in the battery gets transferred to the electrons. So I'm anticipating a mark for chemical energy and electrons. So I've already mentioned them up there. But here, I've wrote them down there as well. Right, what about through the lamp? So, okay, so what you've got is these little electrons are marching their way through the wire. And they get to the lamp. And once they get to the lamp, you've got collisions inside the lamp between the electrons and the metal ions, and they end up getting hot. Now they make the bulb get hot. I mean, so hot that it starts to glow and give off light. That's how bulbs work. Okie dokie, so what about the energy to the surroundings? Well, heat energy will go to the surroundings and light energy will go to the surroundings. So there we go. Right, so hopefully if that comes up, you'll know how to answer it now. Do you see how important this is to practice? I don't want you, right, if this is my student watching this, I don't want you seeing this question for the first time in the exam. No chance. I want you to practice it first, you know? Right, question 11. Answer the question with a cross in the box you think is correct. If you change your mind, blah, blah, blah. Right, which of these symbols is used to represent a thermistor? Thermistor, that one. Okay, this thing here, watch this. D, doesn't that look like a D? I, O, all right? So that's your diode. So this thing here is a diode. Right, this thing is a resistor in a waterproof case with light shining down on it. So that is a light-dependent resistor, LDR. And this thing here is just a motor, an M in a circle. All right, so this thing here, this is the thermistor. Have I got any little tips for remembering that? Yep. I think that thing there looks a bit like a thermometer. You know, like a thermometer's got like a sort of bulb thing on the end, hasn't it? And then if you were to rub that little bit off there, well, there, it looks like a thermometer. Question 12. Figure 12 shows a graph of current against potential difference for an electrical component. These are the graphs that I was talking about before. and that's your positive current up there, which means your negative current's down there because that's 0. And then over here could be like positive 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and then minus 1, minus 2, minus 3, minus 4. So that's all negative numbers there. Which electrical component will show this variation of current with potential difference? Well, as I said before, that's a diode. So a diode only lets current flow in one direction. I like to remember that by looking at the symbol. The symbol for a diode's got an arrow on. That arrow sort of says that current can flow that way, but it will not let current flow backwards. So it doesn't matter how big the negative voltage is, you're not going to get any current flowing. Positive voltage, once it gets to, remember that value there, just in case they ask, is about 0.6 volts. Once it gets to 0.6 volts, then you start getting some current flowing in the positive direction. Right, what about these other things, just in case? Right, a thermistor, right, you won't see a current voltage graph for a thermistor at GCSE level. The type of graph that you will see, it'll just be resistance up the side and temperature along the bottom. Alright, so cold and hot. And the graph goes like that. Low value resistor at constant temperature. Right, well, if that's your current and your voltage, if you've got a low resistance, it'll actually be quite a steep graph. And if you've got a high resistance, it'll actually have a flatter graph. It's the opposite of what you might think. And that's because of the way they've put the axes. They've put I up the side and V along the bottom. Question 13, the last question. Figure 1 gives the names of 3 atomic particles and some descriptions of the charge on the particles and their position in the atom. Draw one straight line from each atomic particle to its correct description. Right, proton. Proton is positive and it's inside the nucleus. So that's that one. I'm going to do neutron first. Neutron is neutral. So it's got 0 charge. So no charge, but that is also inside. So no charge and it's inside the nucleus. So that's that one. And the electron is negative charge, and that's in the shells outside the nucleus. So remember, protons in the middle, P, neutrons in the middle, N, and then orbiting around the outside in the shells are your electrons. Right, well, I hope that's been useful. When I go over the answers, I don't just tell you the answers, I make sure I teach it to you as well. So that helps you to revise, doesn't it? Right, good luck in your exams, work hard, be nice, and bye for now.